Perfeito. Okay. So good afternoon, everybody. My name is Daniel. Nice to meet you. I know that Professor Osvaldo raised the bar up here, so I hope to not let you down. So I work as a materials scientist at the Federal University of São Carlos as a postdoc. And today I'm going to talk to you a little bit about what we have been doing in the interface between glass and data science. My talk is divided into 5 sections. The main content of the talk will be divided into 2 parts. Part 1, you already saw a little bit of a spoiler from Professor Osvaldo's talk, a very nice talk, by the way, where I will discuss a little bit about property prediction of glasses. And on the second part, we will discuss inverse design of glasses. Before that, I will do a brief introduction about glasses, so we can all be on the same page. But before that, I want to start with some first words. So my first word is to thank you for the invite. Thank you for the organizing committee. I was really honored and accepted it right away. So thank you for inviting me. And of course, thank you all for being here, because otherwise there would be no talk. We will all will be in the coffee, right? So thank you. And as you know, science is not done alone, so I will thank all my collaborators. We have right now 3 clusters of collaboration, where it all started at the Federal University, led by Professor Zanotto. So we have a cluster there of people working in the experimental part and on the machine learning aspect. We have a cluster here in the computer department, led by Professor Andrade Carvalho. And we are starting new international collaborations with Professor John Mauro and Dr. Adama Tandia and Colin Wilson. And who knows, perhaps we can start a new collaboration today. Who knows, then you guys will be here, right? So let's start with a brief introduction about glasses. So I hope to convince you that glasses are also materials. Perhaps when you think about glasses, you think about ceramics, because most of the glasses that we use in the daily life, they are considered ceramics, right? So the window glass, the glass on our cars, the glass on our kitchen, they are ceramics, right? But in fact, glasses can be organic, they can be metallic, they can be inorganic glasses, which are the ceramics. But even inorganic glasses, they can be oxides or non-oxides. There is a whole lots of types of glasses that we can make. But for this talk, I will be limiting myself to oxide glasses. This is the focus of this work, right? So when I say glasses, please keep in mind, I'm telling you about oxide glasses, okay? And you probably know this, the main difference between a glass and a crystalline material is its chemical structure. And this is very important. This will be very important for us, right? So a crystalline material has an atomic structure that's periodic, and a glass material has an atomic structure that is disordered. Of course, there is much more to it. This is just a simplistic view, but for us, it's enough right here, okay? Here we are looking at the Material Science 101. This is the most basic fluxogram of material science. What this is telling us? It's telling us that we start with some chemicals, with some composition. We process this composition 1 or more times. After that, we have a material with a shape, an atomic structure. This material will have a set of properties. And depending on these properties, we want to exploit these properties for some applications. This is the basics, right? This is the base for material science. My question is, where glasses fit into this picture, right? Because we need to have a disordered structure, there are some ways to do that, but the most common way, commercially, 99% of the commercial glasses, perhaps even more, are made by the same process. Because you need a disordered structure, you melt your chemicals, and you cool it down really fast. So you trick nature. Nature wants to be in a crystalline state. It's the most stable below the melting point. But if you cool it fast enough, you trick nature, you keep the disordered state, and you have a glass. Most of the glasses are made this way, the commercial ones, right? And if you have the same, most of the commercial glasses, say, commodity glasses, specialized glasses, you name it. And if you have the same process, in the end, you will have a distribution of atomic structure that's quite limited, right? Because it's the same process. Of course, it's not always the same. You have other variables, but in the end, the distribution of structure that you can have somewhat limited. What this means is that the property of glasses are mostly dependent on the chemical structure. And we cannot say this of crystals, right? Because the crystallographic information of crystals will change a lot its property. Think about carbon and diamond, right? Two materials with the same chemical and wholly different properties. This is not the case for glasses. So we have this high dependence of the properties on the composition. Of course, this is a huge simplification, okay? So it's something to think about, to start thinking about machine learning, right? So this dependence here, this strong dependence, is something that we are going to exploit. And we think that this is an opportunity because, you know, you need features, you need information about your material to do machine learning. And if you know that the chemical information accounts for most of it, then this is an opportunity for us, right? And I just want to say that glasses are versatile materials. They can find applications in energy applications. They can find applications in optical things like the fibers that connect us through the internet, right? So we can use glasses for a lot of applications. So they are not only used on in our daily lives, right? And to close this session, I want to show to you that many glasses can be made. In one estimation by Professor Zanotto and Coutinho, they estimated that we can make about 10 to the 52 different glasses. So that's a lot. Okay, perhaps this is overestimated, but even so, if this is overestimated by 10 orders of magnitude, it's still a huge number, right? And we estimate that we have only made 10 to the 6, 1 million glasses have been made and reported. So I wonder which interesting, which fascinating, which technological glasses are hidden away in this uncharted sea of compositions that have never been made, right? And, you know, we want to make them, but it's simply too much. If you randomly make a glass, perhaps you hit the jackpot, but most probably you won't. So we need tools, we need a way to navigate this uncharted territory of unmade glasses faster and cheaper. Because we live in a competitive society, right? We need to do it faster and cheaper. So this is the motivation of what we are doing. So let's start part one. We want to predict properties of glasses because we want to find those glasses that are interesting. So this is the main objective. We want something in our computer where we can feed a chemical composition and it will spit out all the properties of this glass. Okay, easy enough, but how to do it? Not so easy, right? The idea is easy, but how to do it is not so easy. So there are many ways to predict properties of glasses, right? You can go look into fundamental physics. You can go look into quantum mechanics, and you can use these models and predict some properties. And as you move along in the fundamental physics and empirical line, you will find lots and lots of techniques, of modelings that can help us to predict properties. So there are lots and lots of tools in all these tool sets. For this work, we wanted to exploit data-driven modeling because we had a database, so let's see what happens, right? Then you open the toolbox, and then you see that there are lots of methods that you can use that are data-driven. So, okay, where to start? Because there are a lots of methods, we decided to start with the one that we had some familiarity, and that was neural networks. So I'm not saying to you that neural networks are the best. Perhaps they are, I don't know. But we had some experience, and okay, let's keep it simple. Let's go where we have some knowledge and see what happens. But then even so, when you look inside the tool set of neural networks, you will find that there are lots and lots of topologies of neural networks. Which one to choose, right? The main idea, before I tell you the topology that we use it, the main idea of neural networks is connection of information. So you have some information, and it will navigate through artificial synapses. They are weighted, so this information will navigate through them. They will converge to a neuron. Here it's called a cell. It will converge to this neuron. This neuron will grab all this information, make some calculation, and pass this information along through more synapses until some point where you capture this information, right? So it's all about connectivity and trying to find patterns in the data using the weights of the synapses. So as I said, we have lots and lots of topology because these connections can happen in lots and lots of ways. But for this work, we decided to go to use a very simple topology that is sometimes called multi-layer perception. Here is called deep feed-forward. It's the same. Basically, it's a topology where information only goes forward, only goes one way, and you can have one or more layers of these neurons, of these computing entities that are called neurons. I'm not going to explain on details what are or neural networks or what they do. If you are a visual learner, I recommend these two series, Neural Networks Demystified by Welsh Labs, and But What is a Neural Network by Blue Brown. They are really visual, so if you learn better this way, I recommend these two series, right? And if you are a vision learner, I also recommend this TensorFlow playground, where you can see what's happening inside the network. You can change the number of neurons, the number of layers, you can change the activation function, and you can have a connection with the network and understand what's happening behind the curtains, right? So this was our question, how to solve this problem, and we decided for this work to use a neural net. And I repeat, I'm not saying that this is the best, right? This is what we tried. Okay, so we need data. It's a data-driven modeling. We need data to feed the neural net. Fortunately for us that work with glasses, especially oxide glasses, we have CyGlass. CyGlass is a database that collects over 400,000 glass compositions. It collects optical properties, thermal properties, mechanical properties, you name it. Back when we did this work, this was a closed database, but right now it's open. So this is quite interesting because I wish to see lots and lots of new works exploiting this very fascinating database. After having choosing the database, we need to choose our target property, right? So for this first work, we decided to predict the glass transition temperature. Just as a refresher, the glass transition temperature is a temperature where below it, the atoms of your glass, they are frozen, right? They do not move. And above the glass transition temperature, actually you don't have a glass anymore. It's a supercooled liquid, and the atoms of the glass, they can move freely, right? It's an oversimplification. I know TG is much more than that, but it's good for us today. So this was the query. So we looked in all these entries to find those that have TG. Of course, not all of them have TG. Remember, we are dealing with oxide glasses. So we limited the query only for those compositions with more than 10% of oxygen, of atomic fraction of oxygen. And as we need examples to train the network to find patterns, we discarded those compositions that were made with chemical elements that appear in less than 1% of the database, right? So perhaps a glass with plutonium. Okay, fascinating, but only 10 glasses were made with plutonium. It's less than 1%. Let's cut all these glasses with plutonium, right? Because we want example. We want to learn patterns. We need to have a minimum threshold. So here it is. We collected a little bit above of 55,000 examples. And if you look into the data, you will see that we have collected data with 45 different chemical elements. Of course, there are no glasses made with all of them, but among all of them, there are 45 different chemical elements. And of course, you will see oxygen here because it was part of our query. But if you are in the area, you will see that most of the common elements that we use to make a glass are here, like silicon, boron, phosphor, lithium, sodium. Okay, so the most common elements, they are all here. We got that covered. Let's look into the data. This is the distribution of TG, of the glass transition temperature. You see that the most frequent value is about 750 Kelvin. And we have very few examples here for extreme values of TG and few examples for lower values of TG, which was expected. But it's interesting to always look into your data before you start doing something. And this was something that we were quite curious. We wanted to check how many different chemical elements made the glasses that we were studying. Okay, so you see that most of the glasses were made with 4 different chemical elements. So oxygen, because it was part of our query, and 3 other different chemical elements. But look here, above 11 chemical elements, there are only few glasses that are made in this multi-component region. Only 10% of our data set lies here. So this is something that piqued our interest because, okay, there are so many possibilities here and people are not exploring this. So we hope to be able to explore these multi-component glasses once we are able to predict the properties, right? Another thing that we need to look is the scatter of the data, right? So here I'm showing to you the system of sodium oxide and boron oxide. So here is pure boron oxide, and here you are increasing sodium. And you can see how TG changes, but look at the scatter. There is a huge scatter here, right? If I zoom in here from 10 to 20% of sodium, you can see that there are regions with more or less 100 degrees of difference of the glass transition temperature. So that is a lot. We have a database with a lot of scatter, right? And there are many possible reasons to explain this. I will not get into the details, but bottom line, we have a very sparse data set, and we need to work with it. So before we move on, we wanted to quantify this scatter. So we proposed this relative neighborhood deviation. I'm not getting into the details here. You can see in the paper, but we concluded that 95% of all the glasses that we have, they live in a region where the scatter is 6% or lower. 95% of the glasses lives in a region with a scatter of 6% or lower. So we cannot do better than 6%, right? Because otherwise we would be overfitting the data. And this is a huge problem. So this was something to keep in mind. We cannot do better than 6%. This is our intrinsic scatter with this analysis, right? Okay, fascinating. We looked into the data. Now we need to build the network. The first question that I had was how many neurons we will use, you know, because you can change the number of neurons, you can change the number of layers. How many to use? And then I learned a little bit, and I discovered that each problem will have a different topology of network. So even if you are within the multi-layer perceptron, each different problem will need different number of neurons, need different activation function, different number of layers. And how to discover this? How to find the best topology for your problem? And to do this, we used this hyperopt module. This is a Python module, and this navigates through this space of possible topologies. It navigates this intelligently. So it tests a few random topologies, and then by this tree structured parsing estimator, it can make it can suggest new candidate topology to test. And this is what we did, and we tested 500 different topologies, and we chose those that had the best median loss in a 10-fold cross-validation test, right? So we test lots of topologies, found the best one, went with it. And this was the setup. 80% of the data was used for training the network, 10% for validation, and 10% was a test set. It was hidden away. It was locked in a box. The network never saw this, ever. Okay, so this is the idea of this is to simulate new data. Of course, we are not going to make 5,000 glasses just to test our network. So we hid some data to check what happens. And here, you probably saw this plot the last talk, right? So this is the prediction of TG versus the experimental TG for the test set. The data that the network never saw. And it was quite good. It was quite good. At least it was not perfect, but it was reasonable. With a very nice R-square, and you can see here the relative deviation. You can see that 95% of the data can be described by an error of 9% or less. Remember that that the intrinsic scatter was 6%. So we got 9. Not perfect, reasonable. What I want to say here is that, of course, this network will not substitute experimental measurement. The error in an experimental measure is much less than this. It's much less than this, right? It will not substitute. But to give an initial guess, it's something that's valid, right? We were also interested, as I mentioned, in multi-component glasses. So we wanted to check if the network had some kind of trend in the error of prediction as you increase the number of chemical elements in your glass. And there was none, right? So here, the number of chemical elements is increasing, and this is the error of the prediction in the test set, and there is no trend. So we were quite happy because we want to make multi-component glasses, right? So this trend was quite good for us. However, when you look at the prediction versus the true value of glass transition temperature, you will see that our network is not good at the extreme, right? We are not predicting the extreme values of TG quite well. This is a problem. Remember that we had very few examples with high TG, so this is something that we need to think about. And actually, in a new paper, we tackled this problem. I will talk a little bit later about this, but this was a problem in the first paper. Well, you need to look inside, right? If there's a problem, there's a problem. What can you do? And just to show you the prediction of the network, here we are not talking about the test data set. This is all the data points in the data set. And here's the prediction of the network. This is for the system sodium oxide and silicon oxide. And we, as glass scientists, we expect the TG to fall down in this system because the sodium will break the silicon network. You have more mobility, and TG will fall down. So this was expected, and the network learned this. And you can see that even the scatter, the data has lots of scatter, and most of them are within the uncertainty of the network. Now this plot, we already saw this plot. This was the boron oxide with sodium oxide. And this is a very weird system because TG increases, has a plateau, and then decreases. And this is the boron anomaly. This was something that researchers in the last century were crazy because why is this happening? And because they studied it a lot, it got the name of boron anomaly. And we wondered, have our network learned the boron anomaly? And the question is yes. We didn't teach it directly, but it learned from the data that there is an anomaly for boron. It's not just decreasing the TG as it is for silicon. For boron, it learned this. And quite interesting, here you can see our prediction for a purely data-driven model with a physics model. They are not the same, but they give quite good predictions, right? So a comparison between physics and data-driven is giving very nice results. I find this plot fascinating. And just to show you that the boron anomaly was captured for other systems, here is for lithium and boron, right? Here is a network predicting the boron anomaly. So we were quite happy. And of course, this is the result. We now have a neural network that you can throw into the computer some chemical composition, and it's really fast. It gives you the TG. Great. This is what we got. We got this. We published it in the late 2018. This was a collaboration between two CPIDs, the glass CPID from Professor Zanotto and the statistics CPID here from ICMC. And this, believe it or not, this, as far as we know, was the third paper that applied artificial neural network for glasses. So people in the glass community is, right now, it's booming, it's a hot topic, but back in the day, it was the third, right? So it's starting right now. And what we're working right now, of course, for TG, it gave us a good result. So now we want to predict all the properties. Okay, so it's the logical next step. However, we as materials engineers, we do not sell composition. We sell properties, right? The consumer, they don't care if the material has silicon, has boron, has chromium. They don't care. Of course, if there is a toxic compound over there, then they care. Okay, and this is good, but they don't care otherwise. So how do we sell properties? We need to go the other way. We need to go the other way. We need to tell the computer that, oh, hey, we want this set of properties. Now give me some glass that can make this. And this is what we did here. And this is what we are doing. This is an ongoing work. It's still not published, so it's still rough on the edges. But I want to show to you. This is part 2, inverse design of glasses. So how to do this? I'm not a data scientist. I'm learning a lot, but this is not my formation. As far as I know, you cannot use a neural network to do this opposite direction. This direction you can, because one chemical composition will have only one value of TG. But if you give one value of TG, you have lots of compositions that have the same value of TG. So, and neural networks are deterministic, right? So I don't think neural nets are the answer here. We need to go, we need to look into optimization algorithms, right? And there are many tools that we can use here, that are here. Perhaps we can use grid search, okay? So we can test almost all the glasses and just store all this data. And when you want a glass with a certain property, you go and query this data. But this is not good because remember that I told you we have lots and lots of glasses that can be made. So even a very scarce grid search will take a long time. It's a lot of calculation, right? So grid search is out of question. Perhaps we can do a random search. And for simple problems, I think it's possible. Because, okay, you want a simple glass with a TG of 800 degrees, okay? It's quite simple, but as you increase the complexity of your constraints for your material, then you have fewer and fewer answers, right? So it will be quite difficult to find them via random search. It's like the proverbial, you know, the story of a million monkeys typing randomly, right? At some time they will write Shakespeare, but it will take a long time, right? This is what I think is a problem with random search. So for this work, we went with genetic algorithms, not because they are the best, but again, because I had some knowledge about them. So, okay, I already know a little bit. So let's start with what we know. Perhaps they don't work. Let's see. So for this work, which solved with genetic algorithms that are loosely based on evolution theory proposed by Darwin. And the idea is, okay, you don't need to test all the glasses. Perhaps you can start with some random glasses, some random compositions. Some of them, by happenstance, will be better than others, right? And then you somehow evolve these compositions into a solution, right? And this is what these algorithms do. They evolve through means of survival of the fittest. And I'm going to try to do a genetic algorithms with you. I know that, I guess most of you know about it, but when I did my grad and undergrad studies, I never had a class about this. And when I learned about this, I thought this is fascinating. So if you already know this, please bear with me, but it will take a few minutes. Let's try to do this because I think it's interesting. So the idea is that from the biological point of view, individuals have some place where they store the information about themselves. And this is the genotype. This is our DNA. And the manifestation of this DNA is the phenotype. So if you have the color of your eyes depends on the environment, of course, but it's written somewhere in your DNA. How can we translate this for materials, right? So perhaps the genotype can be the composition, right? If I give you this genotype, you can go to your lab and melt this glass, and you know everything that you need to know to make this glass. But what you perhaps don't know is the properties of this glass, and this is the phenotype. So perhaps you don't know that the TG of this glass is about 750, but it is. It's there. Within this information, there are lots of properties that is encoded here, that are encoded here, right? And of course, one glass is an individual, and many glasses are a population. So the idea of genetic algorithm is to start by generating a random population. Here it is. I will just color code them because it will be good for us later on. And we need to define, as in nature, we need to define a fitness function. And this will depend on the problem. So for this problem, for this example, I want to find a glass with a higher value of TG. So my fitness function, I want to maximize TG. But this function can have more than one objective. Perhaps you want to maximize TG and reduce density. I don't know. It depends on where you want to apply this glass, right? So for this simple example, we want to maximize TG. And here it is. These are the glass transition temperatures computed using the trained networks. I'm not cheating here. These are actually predictions by the network, right? And you see that by happenstance, some of them will have a higher TG than others. This, due to the random nature, this is expected, right? So what we want to do is that we want to propagate the information of those that are better. We want to propagate this to the next generation. So we will have some bias in selecting the genes of the glasses. You can see the colors here. We will select most of these genes to build the next generation, and less of the genes of those that do not have such high TG, right? So we've built ourselves generation 2. Last step, we need to add some variation there. And one way to do this is by mutation. Same as in the natural world, right? So you saw here, this was 1. By chance, this was changed to a random number. And you see that this number was not even in the initial population. This was a mutation. Okay? So this is a way to induce variance into the generation, into the process. After this, generation 1 is over, and the process begins again with generation 2. Again, we compute our fitness, in this case is TG, and look there, we have a breakthrough. We have one glass with a TG that's higher than all the previous ones, right? This is what we expect. And as you iterate in this process, we expect to find, if there is a solution, we expect to find the solution. It's not a guarantee that we will find the best one, but at least a good one. If there is, we can find it. And all of this was done using the deep module from Python. This is a fascinating tool, so if you are into Python, check this out. And now, let's go back to glasses, right? What we did is that we applied this concept to try to design glasses, new optical glasses, and new glasses with homogeneous nucleation. I will explain this later, but keep in mind that this is a work in progress. We are still learning, we are still doing, but let's see what we got. Let's start with the optical glasses. So if you want to design a new optical glass, I recommend reading this paper by Peter Hartman, where he discussed just that. He discussed the current trends of optical materials, right? And you can see them here. We want glasses with high refractive index. We want glasses with high Abbe number. We want glasses with high refractive index and Abbe number. And high refractive index and low Abbe number. Bonus point if you have lower TG, because then you can use for precision molding, right? So these are the trends, and according to Hartman, this is the dream, right? To find a glass with high refractive index and high Abbe number for application in lenses. And here is the Abbe diagram. You can see the refractive index growing in this direction, the Abbe number growing in this direction, and what this trend wants are glasses that push the envelope in this direction. This is what this trend wants. And we tried, and we failed miserably. We just could not find any glass that met this criteria. It was really hard. But it was bittersweet because people have been looking for glasses here as far as optical glasses go, you know? This is the dream. So we're not getting it. Perhaps it's a clue in the direction that I'm not going to say that it's impossible, but it's really, really, really hard. Okay? So, okay, we tried, no answer, so let's move on. We tried this simpler design trend. So we want glasses with Abbe number above 60. This can be used for lenses for precision molding, for using in cell phones, right? So we tried this, and lo and behold, this was the first glass proposed by a genetic algorithm in our lab that we melted. This was the first one. Great, we have great expectations, and it was too hygroscopic. We could not measure the optical properties because the ambient, it attacked the glass. It became opaque, so we could not measure. But if you look at the composition, it has a lot of phosphor oxide, so we should have known better. But we were so excited that this was the first, we tried. This was not good, but one thing that I forgot to mention is that into your fitness function, you can apply some constraints, you can apply some penalties. So we just said, okay, let's have a penalty for those glasses with too much phosphor. We do not want to remove phosphor from the search space, but just include some penalty. So the system will try to avoid phosphor. And this is what we did. And this was the second glass. And as you can see, the composition is quite similar: phosphor, strontium, silicon, and aluminum, but much less phosphor oxide, and 80 other compounds. So this is a multi-component glass. This is what we wanted all along. This is the glass. It's much more resistant to chemical attack, and we got it. We predicted a Abbe number of 64.7. No, sorry. We predicted an Abbe number of 65, and the experimental value was 64.7. So it's close enough, right? Let's give the network that. It was close enough. Unfortunately, the TG was a little bit higher. We wanted something in the range of 500 C. So this composition cannot be used for precision molding, but we are still studying other technological applications that perhaps this can be interesting, right? But the search continues. The algorithm is still running. Let's see what it gives to us. Okay, now, in our lab, we work a lot with crystal nucleation. And, you know, I told you that below the melting point, the nature prefers the crystalline state. It's the most stable one. So you need to trick nature into forming a glass. But if you give energy, if you give time enough, the glass will crystallize because it's the most stable phase, right? It will reduce the Gibbs free energy. So this is the process of crystallization. But crystallization can happen preferably at defects. This is called a superficial crystallization or heterogeneous nucleation or surface nucleation, or it can happen in the volume. So it can happen inside the material, even without defects. And this is the homogeneous nucleation. Most of the known glasses, they are heterogeneous glasses. So crystals appear mostly in defects. So, okay, let's try to exploit this. Let's try to find new homogeneous glasses. This is what we thought, because this is what we study in the lab. And we know that there's a very simple rule. Usually, if the reduced glass transition temperature, that is Tg over the melting point, if this is below 0.6, then you have a higher chance to nucleate in the volume. So we know this. This is actually a paper from our group. We know this, so we set this as a target. We want the genetic algorithm to search for those compositions that meet this criteria here. In this test, we applied some extra constraints because we want to be able to melt this glass in our lab, and this is the limit of melting of the furnace that we have. We want the composition to form a glass, so we penalize those compositions with that do not have enough glass formers. Not all chemicals make a glass easily, right? So we know those that make, and we penalize those compositions who do not have a minimum of glass former. For this work, we looked for simple glasses, only those made with 2 or 3 components. Because as you keep increasing components, one of them can act as a nucleating agent, and we don't want that. We want true volumetric nucleation. So we limited to simple glasses. And because we were going to make in the lab, we avoided toxic elements. So these were the first 3 candidates that we tested, and the first one was a success. This is a glass made with calcium, manganese, and silicon. This was a success. The next one did not form a glass, so it didn't melt. So this was wrong. Our prediction of the liquid's temperature was wrong, which we are not even that said, because predicting the liquidus temperature is really, really hard. Our uncertainty in predictions is huge, because the liquidus temperature depends on the crystalline structure, and we are not feeding this information into the network, right? So our prediction is really rough for the liquidus temperature. So this one didn't melt. Okay, patience, next one. And the next one was too hygroscopic. So perhaps these two do have nucleation in the volume. We don't know, but we cannot say for certain. So this is some of the problems that you have in this field, because how can you put a constraint on chemical durability? How can you put a constraint? You know, you will have the uncertainty of your networks all stacked together. So it's, you have some positive results, you will have some negative results. This, we saw that this is pretty common in this, using this technique. Now we wanted to go even further. We wanted those glasses for which the chemical composition of the crystalline phase is the same as that of the glass, right? In other words, there exists at least one stable crystalline phase in the world reported that have the same composition of the glass. But this had to be done manually. So the genetic algorithm spit out lots of compositions, and we check it, because I don't know how to do this automatically. Perhaps using what Professor Osvaldo said, perhaps using some machine learning that can read papers and check this information. But for now, it's still out of my grasp. So this was not machine learning, it was humanly done, right? So we did this, and these are some of the candidates that we got. And if you are in the area of crystal nucleation and you look at this list, you will see that all of those compositions are already reported in the literature to having volumetric nucleation. So all these compositions, they do have volumetric composition, and they meet all our criteria, and they were predicted by the genetic algorithm. Okay? So these are all positive results. We don't need to test, because we have papers published about this. And these were some new compositions, no papers published. And we tested some of those. The first one is a lithium aluminum silicon, and unfortunately, it did not crystallize in the volume. So it was a negative result. But the next two that we tested, this barium silicate and this other barium silicate, they both nucleate in the volume, and are new compositions, and they have at least one stable crystalline phase that is similar to the glass composition. So we got two new results. Those in the last slide, they already reported. We got two new results, and one of them is right now a subject of a master thesis. So there is a master thesis that's studying the crystal nucleation in one of the glasses predicted by machine learning. So, you know, it's everything is feeding itself. So I want to say some closing words. Of course, we are working with lots of other projects, but the week before the last one, we got this paper accepted where we tested other machine learning algorithms to predict TG. So there are random forests, decision trees, K nearest neighbors. So many algorithms, we solved the problem of the extreme values of TG. And also, we tried to interpret the results of the random forest. So in other words, the algorithm, the computer learned something about glass. Now we want to learn what the computer learned. We want to have new insights about the final model that we got. And I'm not going to talk about this today, but this is published, so if you're curious, please check it out. And of course, I want to thank again all my collaborators, and thank you for watching until the end, and the sponsors. And If you have any questions, please let me know.
Oh, thank you for the nice talk.
Thank you.
Can you try to use the genetic algorithm to find a target TG? For example,
Sorry?
If you want a material, if you are a target TG,
Yeah.
can you use the genetic algorithm to
Sure.
because you show only results to maximize it.
Sure, you can. One way to do this is perhaps you can compute the distance between the TG and the TG that you want. So you minimize this distance. So you will find only your last result will be glasses with a specific value of TG. Yes, you can. And you can do this with multiple targets also. So you want a specific value of TG, a specific value of refractive index, of density, you name it. You can have multi objectives. Thank you.
So last week, a friend shared with me an article explaining the science behind the Lycurgus cup, which is Lycurgus cup. It's a piece of art made from glass, and it's very interesting because the light that is reflected is green, but the light that goes through the glass, the material, comes out red. So it took us like I'd say 1,500 years to develop our modern science, to discover how a craftsman back in the day had the ability to develop a material like this. And they discovered that this very specific aspect of the material is due to the nanoparticles of silver and gold in a very specific concentration and also a very specific size distribution. So I'd like to know if technology like this could be able to also predict this kind of properties and also evaluates, I think, not only the composition of oxides, but also the composition size distribution of metals in the material.
Okay, let me think. Your first question was if artificial intelligence can help us to predict what happens in this piece of art, to build new pieces of art that we still have not built. I guess perhaps yes, but right now it's much more rough than that, right? So right now I would bet a better understanding of physics will do you better than machine learning right now. Perhaps in the future, who knows? And your second question was about other materials, right? Not only oxide glasses. Of course. This is not limited for oxide glasses. We just limited ourselves with oxide glasses because this is what we know in the lab. This is what we work in our daily routine. But we are trying to predict for other glasses. For instance, SciGlass has data for non-oxide glasses. Not that much, because they are not as easily done as a silicate, as oxide glasses, but they do have the data. So we are going to try that. And metallic glasses, we have some data. I want to tackle that, but there are lots of stuff going on. Perhaps other people will do that first, but it's totally possible. Thank you.